Hi everyone, I hope you're having a good Wednesday. I hope you got to sleep in a little bit this morning and that you're ready to learn a little bit today about imaginary numbers. This is 7.5 in your book, and what I want to do, my original intent was that we would do kind of an intro today on Wednesday, and then tomorrow, Thursday, would be kind of going a little deeper into complex numbers. But I think that I'll probably be coming back to a lot of questions. So what I'm going to ask you to do is watch this video in class today and do the worksheet. And then if you have time, watch the next video of the next lesson as well. Or if you don't, you can watch it tonight for homework and then bring your questions tomorrow. And if there are no questions on anything else, then I'll talk more about complex numbers and imaginary numbers just because it's just a little bit of a confusing topic sometimes for students. So let's just take a look at this quick intro first. So asking the question, can we solve x squared plus 1 equals 0? So think about that for a second. Could we solve x squared plus 1 equals 0? And if we think about it, there are a couple methods we've been talking about this year that we can try to use here. One is we could look at a graph. Well, if you look at a graph of x squared plus 1, remember x squared just looks like this. It's just a parabola. That's just x squared. And then x squared plus 1, that plus 1 will raise it. Remember, that's a vertical shift up 1. And I know, chapter 2, it was like a long time ago. So that's up 1. So our new parabola is going to look like that. That's x squared plus 1. Well, you notice the issue here is we're trying to get it to equal 0. We're trying to make this function equal 0. So that means we're looking for the zeros of this polynomial. And what's the problem here? Well, there is nowhere it touches the x-axis. So we have no x-intercepts, which means we have no zeros, which would say that this is unsolvable. Let's try it another way. Let's try solving this for x. Let's just subtract 1 from each side. Get rid of that little line there, maybe. So we subtract 1 from each side, that goes away, and we have x squared equals negative 1. Now, that should ring some bells right away that this is not possible with a real number, because when you square a number, it's always positive or 0. There's no way to get a square to be a negative number, because a positive times a positive is a positive number, and negative times a negative is also a negative number. A last way you could think about this is to solve this, we could take the square root of both sides. So I would have x equals the square root of negative 1. But you guys should remember from algebra that you can't take the square root of a negative number. So what that leads into is exactly this guy right here. This is called an imaginary number, or we call it the imaginary unit. And we use the letter I to depict or to denote the square root of negative 1. This guy's called the imaginary unit, or I. We'll just call it I in this course for the most part. So big thing here to write down is that I is equal to the square root of negative 1. So I is equal to the square root of negative 1. And there are a few other ways that you see this defined sometimes in different textbooks. And really the important thing about I being the square root of negative 1 is what happens when we look at I squared. So we're looking at I squared, which is the square root of negative 1 squared. And because this is kind of a new territory, looking at this square root of a negative number, let's talk about a couple examples that will get us to this idea. So if we have like the square root of 25, we want to square it. Well, that's the square root of 25 times the square root of 25. Square root of 25 is 5, so this is 5 times 5, which is 25. Hey, that's what's under the root to begin with. Let's see if that works with another one. Let's try the square root of 49 squared. Well, square root of 49 is 7. So, I'm a little ahead of myself there. So square root of 49 times square root of 49, that's what squared means. Just multiplied by itself. Well, that's 7 times 7, which is 49. Once again, that's what's underneath the radical. So if we look at I squared, that's just the square root of negative 1 times the square root of negative 1, which is going to give us, once again, just whatever is underneath the radical. That's just going to be negative 1. So this idea that I squared is equal to negative 1. So that would actually solve our equation, x squared plus 1 equals 0, because I squared plus 1 would be negative 1 plus 1, which is 0. So these imaginary numbers, the reason they're called imaginary is because there is no real number that solves equations like this. There's no real number, so we need an imaginary one to do this. And it's kind of weird to think about because some people say, oh, it's an imaginary number. They don't even exist. Why do we study these? There are actually a lot of applications. Quantum mechanics and electrical engineering use imaginary numbers a lot. All kinds of fun applications of imaginary numbers that people never really thought would happen. But we need them to be able to solve equations like this. So where you usually see I is if you have something like the square root of negative 36. Now we can't take the square root of negative 36, but we can think about this as being as the square root of negative 1, keep doing that, negative 1 times 36. Then, if you remember from advanced algebra, you can pull out that square root of negative 1 times the square root of 36. Well, square root of 31 is I. That's how we defined it. So this will be written as I times the square root of 36. The square root of 36 is just 6. So that's just I times 6, and convention is that we write the I after, so it's 6I, kind of like an X. So you put it after the number. So square root of negative 36 is 6I. So square root of negative 49, what do you think? Yeah, it's going to be 7I. So basically, whenever there's a negative, just pull out the negative. It's going to be I. So if you have like the square root of negative 5, something like that, well, we can't take the square root of 5, but the way you would write that is I times the square root of 5. Just pull out the negative, and then you have the real number right next to it. All right, let's take a look at an example using I. So if we're looking at something like this, looking at I root 5, that's the last number we had in the example actually, and we're going to want to square it. Well, that's just I root 5 times I root 5. Now, because multiplication is commutative, that means we can rearrange the order however we want. We could write this as I times I times root 5 times root 5. Well, I times I is I squared. Root 5 times root 5, all those double roots we were talking about last time, square root times the square root is just going to give us 5, right? Because we're taking the square root of 5 and we're squaring it, so that's just 5. So I squared times 5. And we said I squared is negative 1. So it's negative 1 times 5, which is just negative 5. So we actually, what we've done here is we found a square root of negative 5. We found a square root of negative 5. It's I root 5. That's kind of cool. All right. So complex numbers, a plus bi. This is how you always see imaginary numbers written. So a plus bi, what's going on here is we have a real number here, a, and b is also a real number. So each one of these are going to be real. A and b are both real numbers, and then I, remember, is just the square root of negative 1. So for example, I don't know, 2 plus 3i is a complex number. Complex because we have a real and imaginary part. So that's why they call it a complex number. It's not simple or real or something. It has a combination of the two. So we have a number from the real numbers, 2. And then we have another number from the real numbers, 3, and that's multiplied by I. So what we talk here sometimes about the real and imaginary parts. The real part, the real part is a. So whatever the a part is in a plus bi, the real part is the a. The imaginary part, now it's tempting to say it's b times I, but it's just b. So the real part and the imaginary part are both going to be the real numbers. So in this case, the real part is 2, and the imaginary part is 3. We don't put the I there because it's implied. If it's the imaginary part, we know it's going to be multiplied by I. So just a little intro there to complex numbers. All right, let's take a look at some examples with complex numbers. When we add and subtract complex numbers, or do any kind of operation with two complex numbers, it's convention to always write the solution in a plus bi form. So if there is some kind of a disconnect, or at some point you have to combine like terms, you have to end up always writing your final solution in a plus bi. So let's just talk about how we add two complex numbers. So looking at these two complex numbers, 2 plus 3i plus 4 minus 6i, this is exactly the same as the problem, 2 plus 3x plus 4 minus 6x. So x, like the variable from algebra, it's exactly the same as how we do this, because I is the square root of negative 1. This is just like a multiplication. So think about these two as being like terms. All right? And these two are also like terms. So we have the real parts and the imaginary parts. So we're going to add the real parts. 2 plus 4 is 6. Then we have 3i minus 6i, which gives us a negative 3i. We notice that's written in a plus bi form. Now, the negative is okay, because that just means that the b is a negative number, so 6 minus 3i is okay. Now this next one, we'll look at our real parts, 1 and 1 and 1, and we're subtracting this time. So remember, we have to distribute that subtraction sign. Remember that from algebra. So we have 1 plus I here, and then we're subtracting 1, and we're subtracting negative I. Well, those two negatives turn into a positive, so we're adding I. Well, look at this. Our 1's cancel. 1 minus 1 is 0. I plus I gives us 2I. Okay. Now, this is a little bit different form that you might see on the homework tonight. So if x is 2 plus 3i, what is 4x? Well, 4x is just 4 times 2 plus 3i. Now, we could write it out, 2 plus 3i plus 2 plus 3i plus 2 plus 3i, and then it would just be similar to these problems up top. But we can also just distribute the 4. So it works just like if this was 4 times 2 plus 3x. So these are exactly the same problem. So that gives us 8 plus 12i. And that's all it is. So multiplication by a constant or adding or subtracting these complex numbers is not too hard. Where it gets tricky is when we start looking at multiplication. So this is a little different. So before, the reason I say it's a little different is because this is exactly the same as if you had an x. But if we look at the i's when we multiply, it's just a little bit different than if we did it with an x. So multiplying two binomials here. If you remember this from 7-1, we just looked at using the box method for this. So I'm going to make a box. And we have 2 plus 3i. Then we have 5, and we have negative 4i. So 5 times 2 is 10. 5 times 3i is 15i. 2 times negative 4i is negative 8i. Negative 4i times 3i, well, that is, let's write it over here, negative 4i times 3i. Kind of like the example we did with the root 5i before. So negative 4 times 3 is negative 12. And then I times I is I squared. Well, what's I squared? You remember that from our definition. I squared is negative 1. So this is negative 12 times negative 1, which is positive 12. So we should have a positive 12 here. That's kind of cool. So we don't have, like, if you did an x with a box like this, if you had x's, you'd have an x squared. But because I squared is negative 1, it just goes away. So now let's add everything together. Let's see. We have 10. That's going to be, and we also have 12. So our real part's going to be 22. Then our imaginary part, 15i minus 8i, is 7i. And we're done. So always writing in a plus bi form. Make sure you don't write those separately, the 15 and the 8i. Now we have one where it's squared. Well, we'll still use our box method. So we have 2 plus 3i. And we have 2 plus 3i. Really tempting sometimes to distribute the square. You cannot do that. Alright, don't do that. Because 2 plus 3i squared means we're doing 2 plus 3i times 2 plus 3i. So we get 4. 2 times 3i is 6i. 2 times 3i will get 6i again. Now 3i times 3i is 9i squared. And I squared is negative 1, so we'll have a negative 9 in here. So let's find our real part here. It's going to be 4 minus 9, which is negative 5. Then 6i plus 6i is plus 12i. And there it is in a plus bi form. I'm going to have to rush through this last one a little bit, but this is something that you're going to see in your homework where I define it as x is a complex number, 1 plus I, and I'm looking for x cubed. So that's just 1 plus I times 1 plus I times 1 plus I. So I'm going to start by looking at the first two together. I'll just make a box. So I'll have 1 plus I and 1 plus I. 1 times 1 is 1, 1 times I is I, 1 times I is I again, and then I times I is negative 1, I squared. So the 1 and the negative 1 cancel, that's nice, so I'm just left with 2I. Right, so I have 2I is that first part right here in the box, that's just 2I. So now that I have to multiply that, 2I, by 1 plus I can just distribute. So I'll have 2I plus I squared, which is negative 1 plus 2I, and I'm done in a plus bi form. So what I'd like you to do now is try worksheet 7.5a, and then after you've done that, watch the next video, which you can find on Moodle. So I'll see you soon. 7.5a, solutions are on Moodle.